Hello everyone, we are the NASA's 2025 Astronomy Surveying the Universe team. Our project, Black Hole Hunters, involves detecting black holes through microlensing events. My name is Anjali Kazmierczak. I am a rising senior and I'm from Yuba City, California. One fun fact about me is I play tennis.
My name is Zoe Kramer. I'm from Eugene, Oregon, and I'm a rising junior. One fun fact about me is that I have a dog.
Hi, I'm Liza Friedman. I'm from Sarasota, Florida. I'm a rising junior, and one fun fact about me is I'm a competitive swimmer.
My name is Olivia Vanicor. I'm from Lafayette, Louisiana. I am going into the 12th grade, and a fun fact about me is that I skateboard.
Hi, I'm Juan Sanchez. I'm from Bronzeville, Texas. I'm a rising senior, and outside of SEAS, I'm a part of the South Texas Astronomical Society.
Hi, I'm Rohan Ravula. I'm going to grade 12. I'm from Srinivas, California, and I like to hike.
Hello, my name is Srinivas. I'm a rising junior and I'm from San Jose, California. And one fun fact about me is I like playing the violin.
Hello, my name is Roshan, Ladha, and I'm a rising senior. I'm from Bellevue, Washington, and one fun fact about me is that I like to snowboard and ski.
This is the outline of the content we are going to be presenting in our presentation.
Black Hole Hunters is a citizen science project started in 2021 as a continuation of SuperWASP, another citizen science project that focuses on identifying variable stars. Black Hole Hunters aims to identify the missing black holes in our galaxy by finding changes in light curves. The 70 black holes that have been discovered were found because of X-ray signatures given off when a black hole becomes close enough to a star to draw in matter and emit light. Black Hole Hunters need citizen contributions to form a list of candidates and conduct follow-up calculations to confirm possible black hole subjects. But finding a black hole using microlensing is rare, so our goal for our research is to answer the question, can we detect black hole candidates using microlensing and predict their mass?
To observe a microlensing event, we use data collected by TESS, which stands for Transiting Exoplanet Survey Satellite. It uses specialized photometers on board to continuously measure stellar brightness. This graph displays how the brightness of a celestial object, in this case a star, changes over time. Moving on, how to read the graph. The x-axis represents time measured in Julian dates, which is a continuous method astronomers use to measure days, providing a consistent timeline for observing celestial events. The y-axis indicates luminosity, or how bright the object appears. The empty white circles are noisy data that later gets averaged out, as shown by the red circles, to make the graph easier to read. Lastly, the symmetrical peaks we observe in the simulated microlensing event indicates that a possible black hole magnified the star, causing an increase in brightness.
Hi, I'm going to be talking about stellar evolution today. It begins with the gravitational collapse of a cloud of gas and dust, forming a protostar. Once nuclear fusion ignites in its core, the star enters the main sequence phase, where it spends most of its life fusing hydrogen to helium. The larger the star, the shorter amount of time it will spend in its main sequence phase. As the hydrogen depletes, the star evolves into a red giant or a super red giant, depending on its mass. Low to medium mass stars eventually shed their outer layers and become white dwarfs, which are the center of a planetary nebula, while massive stars may explode in supernovae, leaving behind neutron stars or black holes, depending on their size. Stellar evolution plays a critical role in enriching the universe with heavier elements and shaping galaxies.
So what is a black hole? A black hole is a celestial object whose gravitational force is so strong that it creates a region of space-time where nothing can escape, not even light, once it passes through the event horizon. As hot gas and dust spiral as a result of the black hole's strong gravitational force, a glowing accretion disk is formed. Also, some black holes launch powerful jets of energy perpendicular to the accretion disk at nearly the speed of light. As a result of their strong gravitational fields, black holes and even other massive objects can cause microlensing.
But what is microlensing? Microlensing occurs when a massive object such as a black hole or a lower mass object like an exoplanet passes momentarily in front of its companion star. Due to the extreme mass of the black hole, the fabric of space-time is warped and acts as a magnifying glass. This causes the star behind the black hole to appear brighter. When the companion star, massive object, and telescope are lined up, photometry sensors simulate a light curve with an extreme peak in brightness and returns to normal.
For our data, we focus on two primary observatories. First, we use data from the Transiting Exoplanet Survey Satellite, which is a satellite-based telescope system equipped with 4 cameras designed to observe regions of the sky with lower star density. This data is available on the citizen science project Black Hole Hunters on the Universe. Our second observatory was the optical gravitational lensing experiment, known as OGLE, located in Chile. OGLE is a ground-based telescope specializing in observing regions with high star density, particularly the galactic bulge.
We used photometric data from the TESS satellite to analyze around 9,000 unique light curves, graphs representing variations in stellar brightness over time. Gravitational microlensing events produce a symmetric and isolated peak in the light curve, as the lens temporarily magnifies the light from the source star. This characteristic peak was the primary feature we were looking for. Because microlensing events are extremely rare, we had to filter through several types of non-microlensing signals, including simulated light curves used for machine learning, light curves with significant data gaps, graphs with instrumental noise or stellar variability, and planetary transits with periodic luminosity dips.
This graph is an example of an unidentified event. The graph presents a linear brightness that peaks and then returns to its normal brightness. A few days later, another peak appears and then once again returns to its normal brightness. When we come across such graphs during classifications, we simply marked the peaks and moved on, allowing for astronomers to easily identify the graphs with peaks and spend more time on classifying the event.
Using the equations governing microlensing, we wrote some code using matplotlib to understand how different variables affect the light curve. Variables like the mass of the lens or the distance between the lens and the star affect the light curve. The first equation, A of t, represents the amplification of light due to the lens. At the peak of the light curve, you can also see when the star and the lens are close to alignment to amplify a lot of light. U of t then represents the angular separation between the star and the lens, and Te, which is the Einstein time, represents the time of the microlensing event. So one of the first variables that are important is the mass of the lens. When we increase the mass of the lens, we can see that the Einstein time, or the time of the microlensing event, increases. But when we decrease the mass of the lens, the time of the microlensing event decreases. And this is because when the mass is larger, it's able to bend more light and increase the time for microlensing. Another important variable is the impact parameter, which is how close the lens passes to the line of sight of the star. When we increase this impact parameter, we increase the separation between the lens and the star, and this decreases the peak of this light curve, which also decreases the maximum amplification. And this is because a lot of the light gets scattered around because of the large distance. But when we do decrease the distance between them, a lot of the light is focused by the lens and gets bent, causing a much higher peak. So now that we understand how the light curves work, we wanted to know how we can actually do more and estimate the mass of the candidate microlensing objects and figure more about the test candidate black holes.
To estimate the mass of the lensing object, we first started with the equation for the angular Einstein radius. The Einstein radius is the radius of the light ring in the sky that is created by gravitational lensing. Then, using algebra and substitution, we derived the equation to find the mass of the lensing object based on some parameters. The parameters are ds, the distance in kiloparsecs from the observer to the star, dl, the distance in kiloparsecs from the observer to the lens, or in this case, the black hole, v, the transverse velocity of the lens relative to the observer, m, the mass of the lens, and Te, the Einstein time of the event.
Okay, let me walk you through how our simulation works to estimate the mass of black holes using microlensing. At the core of our simulation is the equation, which you saw in the previous slide. It allows us to calculate the mass of a lensing object with different parameters. But instead of plugging in just one set of values, we wanted to understand the range of possibilities. So we developed a Python-based simulation that essentially maps out a galaxy's worth of scenarios. We start by modeling our line of sight toward the galactic bulge. This is a dense, star-packed region at the center of the Milky Way, where most microlensing events are observed, and where most of the Ogle dataset originates from. Earth is about 8 kiloparsecs from the center of the galaxy, so we assume stars we might observe are between 2 and 6 kiloparsecs away, positioned somewhere along that line of sight. For each of those possible star positions, we simulate black holes located between Earth and the star at distances ranging from 1 kiloparsec up to just under the star's distance. This is because the closest black hole to Earth, Gaia BH1, is no closer than 1 kiloparsec away. This way, we split the galaxy into a grid of physically valid lens source distance combinations. Using Python for each pair, we calculate the lens mass using our equation, holding the Einstein's timescale constant and estimating transverse velocity using a simplified galactic rotation model. For example, imagine a star located 6 kiloparsecs away. We try black hole positions at 1, 2, 3, 4, and 5 kiloparsecs, and compute the resulting mass in each case. Then, we repeat this entire process for stars at 5 kiloparsecs, then 4, and so on. The result is a complete matrix of theoretical black hole masses that could have caused the microlensing event we observed. This diagram on our slide helps visualize the idea. Every dot in this grid is a possible lens source combination, and the simulation computes the mass associated with each one. Instead of just solving the equation once, we're creating a mass map of possible configurations.
So from our simulation, we took the max mass value from our mass interval, and using the Ogle data, we got the peak magnification factor for all of the microlensing events. Given our mass interval range from our simulation for the lens, we checked if the max value was greater than 2 solar masses, the minimum theoretical mass of a black hole. We then took those points and saw there were 44 out of 545 microlensing events which were possible black holes. From this, we then plotted the max mass of all the lenses from our simulation against the peak magnification factor, which is the maximum brightness amplification during microlensing. From our simulation, we can now see a 4th-degree relationship between the log of the max mass of the potential lens versus the log of the peak amplification factor. This makes sense because as the lensing object's mass increases, it produces a stronger curvature in space-time, causing more light from the background star to be bent, which leads to a higher magnification during the microlensing event. On the graph, you can also see the line x equals 2.5 solar masses in green. And to the right of that line, those are all the potential black holes that we found. And on the bottom, you can also see the 4th-degree regression between the maximum amplification factor and the potential mass.
Now, let's go over the limitations of the model. One of the limitations of our model is that we use the velocities of the Milky Way rotation curve to calculate the relative transverse velocities of the lensing object and the source star. Another limitation is that we assumed that we were always going to be looking towards the galactic bulge. This was to simplify the model.
From the test data, we found 5 microlensing candidates. Using the simulation, we found that the first candidate had an estimated mass of 4.63 times 10 to the negative 4, which is in the mass range of a gas giant. This graph has a very clear peak, so it is a strong microlensing candidate. The second graph had an estimated mass of 7.41 times 10 to the negative 5, which is in the mass range of a giant planet. In this graph, there is quite a bit of noise before and after the peak. However, the peaks are fairly symmetric and clear. The third candidate was found to have an estimated mass of 5.4 times 10 to the negative 5, also in the mass range of a giant planet. This graph has a straight peak, which makes it a strong candidate, but it does have quite a bit of noise before and after the peak. But since the peak is so clear, we counted it as a microlensing candidate. Finally, our last 2 graphs were both calculated to have an estimated mass of 1.29 times 10 to the negative 5, which is a mass range that classifies both of them as planets. Both of these peaks were very consistent and symmetrical. However, the fourth candidate does have a tiny dip when it goes back down, so we are not too sure what it is, but the peak still presents as a microlensing event. All of the masses are in the unit of solar mass. It is important to note that these masses were calculated using our simulation, which presented the most favorable case for identifying microlensing events. We used the maximum value in the simulation. If we used the smallest value in the simulation, our largest mass would become a rocky planet, and our smallest mass would still remain as a small planet, so we would still get realistic results. While the double peak from earlier in the presentation had a clear peak, we were only asked to identify peaked graphs with a single peak by the Scientist Citizen Project.
The comparison of microlensing observation efforts between TESS, Ogle, and the astronomy team reveals notable differences in the detection efficiency. TESS has a 0.002% chance of observing a microlensing event, whereas Ogle has around a 0.00002% chance of observing a microlensing event. TESS has looked at around 1 million stars, whereas Ogle has looked at over 200 million stars, which is a much larger sample compared to TESS. TESS has found around 2,100 microlensing candidates, whereas Ogle has found 3,718 microlensing candidates. In contrast, the astronomy team had a much higher percent probability of observing a microlensing candidate, at a 0.07% chance, whereas TESS had a 0.002% chance. TESS looked at around 1 million stars and found 2,100 microlensing candidates, whereas the astronomy team looked at over 13,000 charts and graphs, but due to duplicates, we only looked at 7,164 stars and found 5 possible microlensing candidates. Microlensing events are rare and difficult to confirm without careful analysis and follow-ups by scientists. Although TESS has already identified some microlensing candidates, the mission is still ongoing, and much of its data has yet to be fully examined. This means the current numbers may only represent a fraction of what TESS might eventually uncover as more data is analyzed and verified.
We were met with a plethora of limitations while searching through the TESS data from the Citizen Science Project. One of the limitations we faced was that there were many variable star graphs that presented as microlensing effects, due to the fact that we didn't have enough time to see the full variations. TESS observes in more than one color in the color spectrum, and if we had access to that information, we could decide if it is a true lensing event. This means that a lot of these graphs require follow-up observations from astronomers. Another limitation we encountered was that there are a lot of graphs within the Citizen Science Project that still need to be classified, so there may be a higher average of microlensing events within those subjects that we have yet to see.
By filtering data for potential microlensing signals through mass constraints and light curve analysis, this approach reduces the volume of data requiring manual inspection and allows researchers to focus on verifying high-confidence candidates. Further research includes obtaining more data about the star to reduce the number of assumed parameters, refining the simulation to look at a broader range of lensing configurations, and extending the simulation to lower mass microlensing events to evaluate the range.
So here are our references.
I'd like to take a moment to share some of our biggest highlights and challenges from our time at SEAS. Let's start with the challenges, because as we all know, growth comes from overcoming obstacles. One of our biggest challenges was learning how to effectively work as a team. With so many different perspectives, it took time to figure out how to collaborate efficiently, communicate clearly, and support each other's strengths. Another challenge was navigating code errors, whether it was debugging or trying to understand unfamiliar code. It pushed us to think critically and be persistent. Lastly, we struggled with finding consistent data. It was a real test of patience and research skills, especially when we were trying to verify the accuracy and reliability of our sources. But now let's switch gears and talk about some of the major highlights of our time that made our experience truly unforgettable. One major highlight was getting to meet people from all over the country. It was amazing to connect with such a diverse group of passionate, driven students. Another unforgettable experience was visiting the Johnson Space Center. Seeing the behind the scenes of NASA's work was incredibly inspiring and gave us a glimpse into what our future in space science might look like. And finally, this program gave us valuable experience for our future careers, whether we go into space, science, engineering, or any STEM field. We're walking away with new skills, more confidence, and a better idea of where we want to go next.
So my experience at SEAS was really fun, and I enjoyed meeting a lot of people from across the nation and meeting people from different cities. I especially enjoyed going to Six Flags in Texas.
My SEAS experience was an amazing journey where I explored datasets and worked alongside passionate peers.
My SEAS experience was amazing. I loved going to the Johnson Space Center and opening up new doors and new opportunities and new ideas for me.
My SEAS experience taught me a lot of new things, and I really enjoyed seeing astronauts in the Natural Buoyancy Lab, and that really opened a lot of new doors for me and allowed me to see a lot of new things that I couldn't see.
My SEAS experience was really transformative. I especially liked going to the Neutral Buoyancy Lab at Johnson Space Center.
SEAS has been an incredible opportunity for me. Over the past 2 months, I've learned so much from completing the program modules to visiting the Neutral Buoyancy Laboratory. These experiences have not only deepened my understanding of space exploration and science, but also helped me clarify what I want to pursue in my future.
My experience at SEAS was amazing because it gave me the opportunity to make connections with professionals and work on real research. Going to the Johnson Space Center in Houston and visiting Mission Control was one of my favorite parts of the internship.
My experience at SEAS has been nothing less than extraordinary. Getting to learn from so many students my age from around the country has been amazing, as they are all so intelligent. I have also enjoyed learning about where my peers are from and their lives outside of SEAS. It was also amazing to learn from so many scientists, engineers, and amazing teachers who are some of the best in their fields. I can't explain how grateful I am for this opportunity. Thank you.
I would like to thank our mentor, Dr. Ries, as well as Ms. Baggio, Ms. Miller, Ms. Tomlin, NASA, the Center for Space Research, and the University of Texas, as well as everyone else who has been a part of SEAS this year. Your guidance, resources, and support have been instrumental in making SEAS possible this year. Thank you.